Hi everyone, welcome to another edition of the Super Spreader Seminar Series. This is the first presentation for the fourth term, but the 13th presentation throughout the Super Spreader Seminar Series, which is very exciting. Now we acknowledge the land the OMNI Network's head office is located on York University. The university recognizes that many indigenous nations have long-standing relationships with the territories upon which York University campuses are located that precede the establishment of the university. And so York University acknowledges its presence on the traditional territory of many indigenous nations. And so we acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. This territory is subject of the Dish with One Spoon, One Pui Belt Covenant, an agreement to peaceably share and care for the Great Lakes region. Now, a little information about the seminar series. So the OMNI Super Spreader Seminar Series welcomes faculty members, OMNI affiliates, and highly qualified personnel, including postdocs and graduate students, to showcase their research, promote their ideas, to share their research experiences, and establish connections among the various branches of the network. And so it is a platform to spread scientific knowledge about the One Health research framework and the research progresses of the 30+ OMNI HQPs with the network scientific research community. And so these seminars facilitate knowledge exchange within OMNI and the emerging infectious disease modeling networks and the collaborating scientific community. Now, we are privileged to have for our first speaker for this fourth term, Dr. Marina Freire-Gormaly. Now, Dr. Marina Freire-Gormaly is an assistant professor in mechanical engineering department at the Lasonde School of Engineering at York University. Her research focuses on the development of an improved understanding of aerosol transmission in indoor environments, considering the HVAC design, the development of stand-alone solar-powered reverse osmosis water treatment systems, and energy recovery systems for remote communities that lack access to grid electricity. She also is interested in machine learning applications for smart design of innovative energy and water systems. Her research interests are also in advanced manufacturing, smart systems using Internet of Things and artificial intelligence, and advanced additive manufacturing methods. She completed her PhD and master's from the University of Toronto in mechanical engineering. Her master's was on pore space characterization of carbonate rocks using microcomputed tomography and pore network modeling for advancing carbon capture and strong technology. She has previously been a course instructor for undergraduate energy-related engineering courses at the University of Toronto. She has also worked at Ontario Power Generation on the Darlington New Nuclear Project and the Darlington Refurbishment Project. She contributed to a World Bank project evaluating Canada's regulatory indicators for sustainable energy. She currently serves as the chair of Student and Young Professional Affairs for the Canadian Society of Mechanical Engineers. She is passionate about research and teaching energy systems to inspire the next generation of engineers to tackle society's growing sustainability challenges. Her research interests include energy systems, optimization, and design for global engineering contexts. And so today we are privileged to have Marina to lead us through this talk. minimizing airborne transmission routes in indoor public spaces using a combined spatio-temporal risk model and computational fluid dynamics approaches. And so we welcome Marina, and thank you all for joining us today. Marina, you can proceed from here. So I will stop sharing and then you can share your screen. Thank you.
Thanks for the kind introduction, Joseph, and for this opportunity to share about my research. I really appreciate it from the OMNI network and Professor Wepping Zhu and colleagues. I'm really excited to share about our team's research and also a bit about the career path that I've had to be able to work at York University today. So we'll give you a bit of an overview of what I've done so far. So my research fields have spanned material characterization, water treatment, and we really pivoted towards COVID-19 aerosol research during the pandemic. And with the OMNI One Health Network, we were able to work with collaborators and really figure out a way to bridge that gap between understanding how those aerosols move within an indoor environment and then trying to develop a risk model for how risky each different setup of the heating and ventilation is, and how we can minimize it by designing the HVAC in a better way. So a bit of my background to give you some context. I did my undergraduate, master's, PhD, and postdoc over at the University of Toronto. And since you might be graduate students attending today, I thought that it would be good to give some context that I think when you're in your graduate studies, it's always great to participate in lots of different projects and try to get the most out of your experiences. So taking on leadership opportunities like arranging these seminars, or maybe in the OMNI One Health Network, you're going to help arrange some of the conference or seminars and symposiums that happen. Because in my own career, I found that it was quite helpful to participate a lot in the graduate student associations and the local Professional Engineers Ontario, as well as the Canadian Society of Mechanical Engineers. That gave me a lot of more context of the work that I was doing and interacting with lots of different people. As well, I took some time to work at Ontario Power Generation for 16 months, and that was a great experience into more of the nuclear side and large-scale energy systems. So it helped contextualize what I was learning in my undergraduate degree on energy systems and see how these large-scale systems work at the provincial level, and also how do we approve new projects like the Darlington New Nuclear Project, and how we can compare safety and quantify the risk factors for these complex energy systems like nuclear power plants. So I also contributed to the Darlington refurbishment, which is pretty much wrapped up now. So it's quite exciting to see these projects that you contributed to finish well and continue providing electricity for society. And I also wanted to touch on the idea that a lot of projects you work on, at the time you might think that it's just a small project, it doesn't have too big of an impact, but many years later you might be drawing on the skill sets that you learned there for newer projects. So this World Bank Regulatory Indicators for Sustainable Energy was a project I had worked on many years ago to quantify how well Canada was ready for installing new sustainable energy. And part of that project involved speaking with a lot of stakeholders in the industry as well as in government. And currently we have a project that many of my grad students are contributing to as well. And we actually are drawing on all those skill sets. And when we're working with our industry partner, they were most excited about our work on that earlier project, even though it was many years ago. All right, so that's a bit of background. So I think everyone's quite familiar in this audience about the research context, but we all lived through the pandemic of COVID-19, and we know that it's airborne transmissible. But at the beginning of the pandemic, it was a bit of a question, like whether the airborne transmission of COVID-19 was a real risk or not. So many researchers did these types of visualizations of a cough, or if someone sneezes, how many droplets and what are the size and range of sizes of those droplets, and how many viruses can even survive within those droplets and for how long. So there was some mounting evidence that really showed that the airborne transmission of COVID-19 was happening. This was a restaurant in Guangzhou, and the index patient is here as A1, and they had COVID-19, and then the people in red all got infected, but there was no evidence of any close contact. Even the staff who were serving the different tables didn't mix in between the tables. They had a very systematic distribution of the food where there was one server for each table, and they didn't mix the dishes or anything. So they knew for sure it wasn't because of contact or formite transmission. So later on, some researchers did a study of the HVAC there. So HVAC is a heating, ventilation, and air conditioning. And as you can imagine, it's pretty hot in Guangzhou. In the restaurant, they need to make sure the air is circulating. So they had an air conditioning system here in the top right corner. And it was creating a circulation loop right above these three tables. So that provided the evidence that all of these people in red had gotten infected because of the airborne transmission. And we also know as we speak or as we eat, we create a lot more droplets than when we're just, say, sitting passively in a lecture hall. But another case that really demonstrated that you could get COVID by aerosol transmission was a Skagit Valley choir rehearsal. So 87% of the choir members became infected, and there was only one person in this red index case that was infected before the rehearsal. And there was no way that during a 1 hour or 2 hour choir practice that one person had shook hands or interacted directly with 52 people. So this was a very large impetus to really demonstrate that COVID-19 was transmitting using airborne transmission. And then there was also a study by Ben Dormalin et al. So they found that 50% of this tissue culture infectious dose per liter of air, they were able to see how long the COVID-19 could survive over time. So for this, it was done for SARS-CoV-1 and SARS-CoV-2, and they were both viable in air for 3 hours, and the air conditions that they had studied were between 21 to 23 degrees Celsius and 40% relative humidity, and these are around the conditions that we typically have in buildings and in environments. So this really justified that, okay, you can have COVID-19 surviving in the aerosols, and those aerosols can be breathed in by other people, and then they can get infected. So there was a large open paper written and signed by 239 experts and led by Maraska et al. That really tried to emphasize that it was time to address airborne transmission and that people should really be wearing masks in crowded places and that there should be a widespread public use of masks. So our research really looks at what HVAC settings affect airborne transmission and what are these environmental conditions like temperature, humidity levels, how about indoors versus outdoors, and then how can we design the heating, ventilation, and air conditioning so that HVAC system in a better way to minimize the risk of transmission. And how can we even make sure that classrooms and offices are safer when they reopen? So there was a large focus on using disinfectants and wiping surfaces, but fundamentally, people are going to be sitting there for maybe 8 hours per day, and whether they're wearing a mask, a fabric mask, an N95 mask, KN95 mask, and what the HVAC configuration is still, even today, there are many researchers in US and Canada that are really calling for improved ventilation systems in elementary schools and hospitals and office spaces. What we've been working on, I'm going to present some of my graduate student Armakan's work, as well as Kishan Webb. He recently graduated from his master's, and Raihan Ali, he's still working on his master's, but he's made some good progress. So I'm going to show all of their recent research. So the goal of this research was to look at the space and HVAC optimization to minimize the risk of airborne transmission. So one area that's very good at this are hospitals. So you can see here, it's an isolation room, and the way they tackle this problem is that they have a negatively pressurized room. They also have very high air exchange rates. So this is the exhaust, and in this diagram, there's two supplies. And the rooms, you can see they're quite sealed, so they're negatively pressurized. And then they also use HEPA filters, and they limit the air recirculation. So the number of air changes, that's making sure that you have really fresh air in the room, and as soon as the patient is even breathing or coughing, all of that will get exhausted up through this exhaust. So we use a combination of computational fluid dynamics modeling, and then we consider where are the likely occupied areas. And it's very expensive to completely renovate a building, so we look at minimal HVAC system changes, but we also care about how can we make it safer for future. So it's quite important to think about how do we design buildings more safely for the future, or even aircraft or buses, for example. So we take into consideration the room dimensions, the locations of the air inlets and outlets, and then the likely occupied areas, and what HVAC system changes would need to be done. So there was an earlier paper by Yin et al., and they looked at this isolation room. So there's a main exhaust. It's a slightly different configuration than the previous slide. And then there's an overhead supply. There's also an auxiliary exhaust and a displacement diffuser. And then this is our simulation work where we try to use their model of all the dimensions of the place and then try to simulate it using computational fluid dynamics. They actually use an entire experimental chamber with many temperature probes and aerosol measurement devices. So they had a very extensive experimental work. So we wanted to experimentally validate our simulations with the results they had already published. So here you can see when the patient coughs, all of these aerosols are generated, and then we can track how far they've flown over the simulation time. And this is the auxiliary exhaust. So many of them you can see are traveling towards the exhaust there. But some of them do get deposited on the floor and on this caretaker. So it's just a rectangular prism, but this represents, say, a nurse or a doctor or a care worker, or maybe even a family member that might be visiting. So we wanted to see how those particles get flowing out of the patient. And then these types of CFD experiments are much cheaper, and they require computational time and computational resources, but they don't require any major experimental chamber. Okay. So part of this work required setting up this computational domain. So it's time dependent. It also used a turbulent K epsilon RNG model, and it also uses Eulerian Lagrangian particle tracking. And the different initial conditions that we can specify were this particle injection from the cough of the patient. And then we also have boundary conditions like these inlets and outlets of the supply and the exhaust and the diffuser location. And then if you were to zoom in on these, you can see there's vectors demonstrating what are the directions of these velocities. Okay. So this was done for a classroom by another set of researchers, and it really inspired our work as well. So they have the instructor at the front. So when you're speaking and you're talking to a class of students, a lot of aerosols are generated as you try to project your voice and make sure that even the student at the back of the room can hear you. And so in this classroom, we wanted to the researchers wanted to quantify what is the risk of transmission to these students that are in the front compared to the back, and what happens if they were to move these HVACs from the front of the room versus the back of the room. So what they found was when it was at the back of the room, far away from the person that's talking the most, then there was a pretty well-distributed risk. But then if you take a cross-section and a plane directly where the heads of those kids are, then you can see the most risk is closest to the instructor, and there's a bit of a hot area for the front student on the far side near the window. And also in another cross-section here, you can see that when you put the ventilation at the front, then we've created it much safer at the back, and for most of the students. Now it's only just this one student at the front. So where you put this supply air does have an impact, and earlier researchers were also able to demonstrate this. This is for a relatively small classroom though, and we know at York University, for example, or any university really, you can have upwards of 150, 300, sometimes even 1,000 students in a given classroom. So this is our model, and this is the Curtis Hall lecture hall. Some of you might have sat in it, and you can see here we have the instructor at the front of the room, and then there's a series of different air inlets and the 2 air outlets, and we have 2 different configurations. So the mixing ventilation is what is already there. You can see that there's some air inlets close to almost every row, and there's 2 air outlets. And for displacement ventilation, this is another methodology of ventilation. It's more common in Europe and a more newer design where you put the inlet air at the base of the chairs and it's closer to the ground, and then your air outlets are near the top. And some of the theories around this is that if you put the air down near the bottom, then by convection it can mix around the room. So in the mixing ventilation scenario, you can see that there's a high velocity vector as the fresh air comes in. And then you end up getting a temperature contour as well for that mixing ventilation. So we looked at putting the infection sources at different locations within the room. So let's say if we put one student at the front, maybe they have COVID and they don't know it yet because they didn't have any symptoms. Then maybe what if they're in the middle, and what if they're in the back? So then we tried to quantify using an SIR model, and by collecting all of the amounts of aerosols at those different locations in the room over a time period of that CFD simulation. And in the mixing ventilation configuration, we found that the highest risk was near that front student because they don't get that much of ventilation if you look here, depending on where they're sitting. So they ended up having the highest risk, but the displacement ventilation performed quite a bit worse because it seemed to spread more of the aerosols around to the adjacent people. And that was for when we looked at just a front infection source. So then I wanted to give you some brief results from the different projects. This one is from Keyshawn's thesis that he recently defended, and he looked at a much smaller domain because he wanted to explore using machine learning and how can we have this, say, an office space, although it's just a really small space, how can we predict and estimate the aerosol transmission in different locations of the room, but without running a really computationally intensive CFD model every time. So these are some of his CFD results for the stratum. So he also included, so when you look at a office room, maybe it seems pretty straightforward and it's just a small room. But then when you look into more details, and this happens a lot in your graduate studies, it might seem very simple on the surface, but then as you dig into it, it gets a bit more complicated. So the person has a certain heat profile. They're actually generating heat. As you know, your body temperature is around like 36.5, and you're constantly emitting that heat into the room. And then your computer also is providing heat into the room. So all of these things actually influence the airflow patterns. And then there's different inlets and outlets on the office. And even when you think about the entrance of an office, there's a door slip. So depending on whether the door office is open or closed, you're going to have a different airflow into and out of the room. So here you can see some of the recirculation patterns that occur within that small office space. And even as a grad student, you probably meet your prof maybe once a week or every 2 weeks. So you might be having a pretty one-to-one conversation in this pretty small space. So these are pretty useful to see. And then you can see when the person coughs in the office, how long the concentration kind of stays around in the room and how long it takes to exit. So then one of the projects that Raihan is working on is trying to model the airborne disease transmission through cough droplet aerosols in an upward moving escalator. So he wanted to look at how the dispersion and transmission and evaporation of the cough droplets at different environmental factors and escalator velocities. So you've probably gone to a mall, or even if you need to use a TTC or the public transit, you need to use the escalator all the time. And some offices even have them. So when you think of an escalator, when there's an upward moving escalator, you can think about what is the effect of the escalator velocity or the effect of the relative humidity. So if it's inside a building, or depending on where that building is, the relative humidity could be different, and also what the environmental conditions are. And then all of these can impact the dispersion of those aerosols, the deposition of them, so whether they land on the handrail or on the stairs, or maybe on the person behind them. And then the droplet evaporation rate is also impacted by the relative humidity and the temperature, as well as the penetration length, so how far down the escalator does it go. Now for the downward moving escalator, he investigated these same velocity and relative humidity and how it impacted those. And then he created a response surface using optimization to figure out what's the best velocity. And he also used this genetic algorithm, which is a optimization tool to find out the best design in a really heuristic problem where you have many inputs and outputs, so you don't have necessarily a fixed linear or a continuous problem. And he was looking at how to decrease the penetration length, so how far down the escalator or how far back up it goes, and decreasing the concentration. So those were the goals. And here, for the effect of velocity, this was for the cough droplet trajectories. And you can see that as a escalator is going upwards at a velocity of 0.4 meters per second, it travels down to around this step. But when it's going at a faster rate of 0.6 meters per second, you can see that the aerosols bounce down the stairs much farther. So this was after 5 seconds of simulations. So at higher velocities, the droplets are able to travel further down behind that infected passenger. We've also been really fortunate to collaborate with a lot of industry collaborators. So de Havilland Aircraft of Canada Limited, and this is actually a really exciting organization there. That's the Downsview Aerospace Innovation and Research Hub. It's located in Toronto, and it tries to bring together suppliers as well as aircraft companies and researchers and students all together to really come up with new innovative solutions to really push the industry forward. Y-Space YorkU is a organization which helps to commercialize technology that's developed in York, and then to smaller companies, Hummingbird Health and TMBN Extrados. And I guess I would just emphasize here, for your career as a graduate student, all your classmates and colleagues as your grad student, you actually have a lot of leeway to initiate new things like seminars, or maybe you want to lead a club that doesn't exist yet, like maybe a chapter of one of the mathematical societies, or maybe one of the like American Society for Mechanical Engineers or Canadian Society for Mechanical Engineering. You can initiate all these types of chapters as a grad student, and then that can help you develop your network. And then later on in your career, your classmates, maybe some of them will start their own company, and then you can try to work with them later on in your life, and also keep in touch, obviously. So I would just encourage everyone to be really collaborative and friendly with everyone that you're working with. And then I really like to share our research widely. So we've had the opportunity to share about the work at City News, CTV News, Radio Canada International, and I think I've done around like 30 media interviews around this topic. So it's something that really impacts everyone's daily life. So I always figure that it's best to share what we found so far and try to really guide the public towards better ways to minimize their own personal risk, and also how can we try to guide some public policy. Maybe more funding can be given to schools to improve their ventilation systems. It's a cost, but I think keeping our kids safe in their daily lives, and the teachers and the staff that are teaching the next generation, is a really important endeavor. We also have this bulletin article in the Canadian Society for Mechanical Engineering, and a couple forthcoming articles on ARMA and Keyshawn and Raihan's research. This one was for a very basic elevator at the very beginning of the pandemic, but then we have a lot more results to share more widely. We've also been grateful for a lot of funding from NSERC through the Missions Alliance grant. This is the collaborative project with DARE and de Havilland, and we're still working on this one to be able to really understand how aerosol transmission happens even in aircrafts. And then we're also working under the Emerging Infectious Disease Modeling Network. So we've been grateful for some funding from the OMNI network to be able to do this research, and also to have a platform to share our work with fellow mathematicians, and a really wide range. I've learned a lot by being a part of this community of researchers and emerging infectious diseases. So I'm really grateful to be a part of this network. These are some of the references that I listed during the talk. And this is my team. I'm really grateful for all their hard work. We've got our grad students here. As alumni are pictured. We also have our postdoc, Dr. Robert Yang, as well as our research assistants, Keyshawn, Felix, and Whitney. And these are some of our past alumni are also in here. So this is Arma, and some other graduated students like Mubaraz and Brandon, and Arma's here too. So this is my team, and thanks for your attention. I open the floor to any questions. Thanks a lot for listening.
Thank you, Marina, for the great talk. It's a lot of information in there. Thank you so much.
My pleasure.
So, yeah, we would open the floor for questions. I see Christian raising up his hand. If it's okay with you, you can mute yourself and talk. And before you start, if anyone is not comfortable talking, you can put your questions in the chat and we can read them for you. Okay, so Christian, you can do it.
Yeah, thank you for the wonderful presentation. It's a lot of great work that you've done. I was just wondering if you could comment a bit on the challenges or the difficulties or the lessons learned when it comes to communicating to a broader population with the public outreach that you've done versus, say, speaking to us or publishing your work in peer-reviewed journals and so on. What sort of conceptual leaps did you sort of need to make in order to have that discussion?
Yeah, that's a really insightful question. I think it is a challenge when you're talking to the general public and trying to not frighten them, but also still give them the information they need to keep them and their family and their friends and themselves safe. So part of it was really understanding what the best practices were in the industry on like the HVAC side, and then also trying to contextualize the information. Like, we don't want to be taking the N95 supply masks from the medical sector, but if you have access to them, then you might as well wear them. Especially at this point in the pandemic, it's quite easy to get your hands on a KN95 mask and just wear it when you're in the grocery store. So I think part of it was trying to understand both the current best practices, and then also contextualizing the research to them, that it's like not to frighten them, but if you have access to it, then you should use it.
It's a fine line. Yeah. Thank you again.
Thanks.
Armel, you can, go ahead.
Thank you for the presentation. It was excellent. I'm just wondering, how much detail do you need to develop a sort of a model for a new environment? So, for instance, you've got a room that you've modeled. If, for instance, you wanted to develop similar sort of simulation models for different geometries, how much detail and what level of information do you need to do that?
So we were quite fortunate with the Curtis lecture hall that we could, thanks for the question. We could work with the York University BPFA, the finance and administration area. They were able to give us the building designs and drawings. So mainly we need the locations of those inlets and outlets of the HVAC, and then the room configuration itself. So it's not too complicated. It just takes some time to put it into the model. So we use it's typical to use SolidWorks to convert those 2D drawings into a 3-dimensional diagram. And then we just need to make sure that the program can run with convergence and be able to simulate the environment.
Okay. Have you considered, or have you looked into sort of exploring more simplified approaches in terms of, for instance, if you looked at northern communities that were quite hard hit by having to sort of live in sort of tighter sort of residences, etc., it may not be amenable to, have very detailed sort of geometries of residences and HVAC flow patterns, etc. But is there any plans to look at how much complexity is needed versus not, and can we make some simplifications to fit for purpose kind of thing?
Yeah, this is an area we're actively trying to improve upon. So Kishan's thesis was trying to see how we can use machine learning and try to predict paths of these particles instead of using a fully developed CFD model. As well, we've also looked at potentially working more on the way more, say like distribution of particles from a chimney stack, and then you can use these more heuristic models and mathematical models of how the flow occurs. It is quite computationally expensive for the CFD, so I think it's an excellent point and something that we're actively working on to try to improve upon.
Thank you.
Thanks.
Yes, if any other person has a question, we still have time to take that. And again, you can drop your question in the chat if that is okay for you. Okay, Professor Zhu, yeah, go ahead.
Yeah, Marina, thank you for the great work and
Thanks.
excellent presentation. Very nice. So in fact, just now we have Amir. He's from Public Health Agency of Canada. He has been working with Nick Ogden, has leading a modeling, of course, not only just modeling group. Just continuing from his question, this is really great. Like you showed how you extend your research from your, your neighborhood, because like where you are, to talk about how the space related and affect the transmission. So this is really you really show a path. I would like the audience can see how you extend your research from your original training and then now expand to a broader application. So for the question, just now Amir mentioned the geometry. So I see now that this result are really helpful. You work with many of the industry. Based on your research, like, do you have any suggestions, or have you reached to that level? You can have suggestions how to improve the geometry design of classrooms or public spaces like airport. Currently, I believe all the designs were not really prepared for controlling or stop the transmission. So with your study, I think you may have general principles as a guide from now on any classrooms, primary school, high schools. So you may develop some general guidelines to next 100 years of design of the space of the geometry.
Thanks, Professor Zhu. That's a good point. And also building on Amir's question earlier, I think I missed emphasizing some of these, but in Arma's work, she was able to really come up with some general conclusions. For example, if someone is at a higher risk, and they don't want to catch anything, they should really be closer to the inlet of that HVAC system into the room, so they're getting a lot of the fresh air. And if someone is sick, then they should be sitting near the outlet, so that as soon as they cough or breathe, their air is going out immediately. But these are if you already know that you're sick or that you're already susceptible. So we're still developing better guidelines and trying to really get those broader perspectives on how we can develop it in a better way. But this is really the overarching goal, is how can we make it safer for future without having to rely on everyone necessarily wearing a mask, or because there are contexts where you actually don't wear a mask. So for example, in conferences, it's quite common it's probably safer to wear a mask, but then you're meeting new people and trying to speak loudly in a really crowded environment. So it's quite common people aren't actually wearing masks. Or as you mentioned, in a airport, there's so many times where you're sitting somewhere and then you're kind of looking. I was traveling recently and I was looking around at the HVAC systems, and it can definitely be designed in a better way, because there's so many times when you're in a crowded place, even that time when you're waiting for lining up to get into the plane, and that corridor is usually very poorly ventilated, if at all, and you just have everyone standing around for sometimes like 20 minutes to queue. So I think there are areas and strategies that we can take for developing these types of broader guidelines.
Thank you.
Thanks.
Okay, any other questions, please? Okay, cool. It seems we are all okay with this. So we want to thank you again, Marina, for this talk. A lot of information in there. We are grateful for also accepting to be with us for the Super Spreader Seminar Series. And we want to thank all of you who have joined today, and we continue to have this series, so keep on joining us anytime we have a talk. All right, so we end the talk today, and then see you all next time. Bye.
Thanks, everyone. Thanks for the great questions and opportunity to present.